Now, to get the webinar started, here is your webinar moderator, Gabriella Giammarco. Gabriella?
Thanks, Molly. Good morning, everyone, and thank you for joining us for this exclusive webinar on the effects of fluid flow dynamics on thermal fluid performance with Paratherm heat transfer fluids. Founded in 1988, Paratherm is a team of service-oriented people with a variety of training, skills, and experience. We specialize in heat transfer fluids, system cleaners, technical services, and fluid analysis in our state-of-the-art on-site lab. At Paratherm, we are all about fluid technology and solid service. Our sales engineers can help you select the appropriate heat transfer fluid specific to your application, while our technical services section can help troubleshoot an ailing process or help to design fluid and system maintenance programs. Today, we're lucky to have our Global Product Manager, Ryan Ritz, here to show us how to overcome the obstacles you'll face when developing a custom solution. Ryan's presentation introduces key fundamentals of heat transfer and fluid flow dynamics as a foundation to illustrate the root causes behind minor oversights that lead to major problems. The significant effects that flow has on thermal fluid performance will be shown through practical representations and supported by scientific rationale. Please feel free to submit questions at any time. For the last 15 minutes of the hour, Ryan will answer as many technical questions as time allows. If we miss your question or run out of time, we will be providing a document the following day with all of our answers. Now I say we let Ryan take this presentation over. Ryan?
Thank you, Gabriella. So, as Gabriella had introduced, we're going to be discussing the effects of fluid flow dynamics on thermal fluid performance. Let's go over a quick overview of the topics. We're going to start off by just reviewing some heat transfer fluid basics. And we're going to move in on the same kind of level and discuss general system design considerations. Now, keep in mind, our topic is flow today, fluid flow dynamics. So we're going to be gearing all of these things back into flow at some point during the presentation. We're going to go into fluid specifications and operating parameters, and then into the meat of the presentation, which is the fluid flow dynamics section. In this section, we're going to be discussing Reynolds number, how that relates to turbulent versus laminar flow in your system. We're going to go over the dynamics of what happens at the film layer of your thermal fluid tubing and the heat transfer that takes place there and why flow is so crucial to that specific area. And then we're going to go over a brief system flow review that's going to show you how heat transfer through the system can be affected by different areas, fittings, different flow areas, pressure drops, and so on. From there, we're going to discuss, for some reason your fluid does degrade prematurely, we're going to talk about fluid and system maintenance reviews. So proper operating practices to prevent problems from happening, and a fluid analysis program that you can run to really know what's going on inside of your system. At that point, we'll go into system cleaners and then overview some key safety considerations. Let's get started. Heat transfer fluid basics. So what are heat transfer fluids? Well, first, they're also known as thermal fluids or thermal oils, heating and cooling fluids, hot oils, sometimes thermic fluids. We're going to be using pretty much the two terms heat transfer fluids and thermal fluids interchangeably throughout the presentation. Just know that they mean the same thing. The key point behind heat transfer fluids and why the technology is so useful is it allows the user to generate high temperatures at low system pressures. Doing this in a safe, low maintenance, and extended operating lifetime fashion, comparing to traditional heating mechanisms such as steam heating or direct fire heating. And lastly, you get highly efficient, non-corrosive performance that allows for accurate temperature regulation and uniform heat throughout the system. Just to clarify what the scope of this particular presentation is, we're going to be focusing on high temperature thermal fluid heating. We're not really going to be talking so much about chilling, although some of the topics do relate to that. And we're going to be focusing on non-aqueous, so no glycols or brines really, natural and synthetic organic hydrocarbon-based heat transfer fluids. And this is all going to be in the form of a closed-loop circulating system. The general system design elements. Now, this is a very basic layout of what a thermal fluid control system looks like. We start off with your heat source or heat sink. This is, for our purposes, going to be in the form of a gas-fired or oil-fired heater or an electric element heater. That's going to be heating the oil to send out into the system. You're going to use a circulating pump to circulate it through the closed loop. And that fluid is going to be going out to whatever your heated process is going to be. So that could be a thermal fluid fryer or a chemical reactor, a reboiler, could be a heated tank, any number of different process applications that need to be heated or cooled. And finally, the last key element of a basic heat transfer fluid system is your expansion tank. Expansion tank allows for the system to stay under low pressure conditions. So as the fluid is heated, the volume expands the fluid out, and in order to keep it under low pressure, you need to have somewhere for that fluid to go, hence the expansion tank. So not only are these the key elements that will make the system work, each one of them has a specific contribution to flow dynamics that we're going to discuss throughout the presentation. So your heat source or heat sink. A fuel-fired heater. Typical design would be that the heat transfer fluid recirculates through cylindrical coils. And most commonly, you're going to have a gas or oil-fired burner, and that's going to fire a flame down to the center of the coil system, heating the fluid running through the coil inside. Now, this is a key area to consider when you're talking about flow, because if you don't have the proper flow through that coil system at the highest temperature concentration throughout your whole process, there's going to create some serious problems there. So when we get into film temperatures versus bulk temperatures and fluid flow through that pipe, we're going to be focused on that coil inside of the fired heater. And you also have electric heating elements that could be the heat source for your system. Now, typical design for this, the electric heating elements are immersed into a circulating fluid. So a little bit different. You don't have the fluid running through the tubes, but you actually have it flowing on the outside of the elements. So this creates another flow situation to take into consideration. When you have a very high energy electric heating element, you want to make sure that the watt density doesn't exceed what your fluid can handle. So typical watt density is going to be maximum 20 watts per square inch. And keep that in mind if you have you're specifying with an electric immersion heater. And that's going to be considering what is typical for a 1.2 to 2.5 meter per second velocity. Some more alternate technologies for your heat source: waste heat recovery system, biomass burner, or a direct expansion heat exchanger. So keying in now on the circulating pump, obviously we're having a webinar about fluid flow. You need to have a mechanism to make that fluid move throughout the system. So brief introduction on the circulating pump. Typically what you're going to see in any thermal fluid system would be a standard air-cooled centrifugal pump. They also have water-cooled versions of this. Your centrifugal pumps are the most robust, low-maintenance options for you to use in a heat transfer fluid system. The limitations on temperature are somewhere around 600 degrees Fahrenheit. Now, these are all standard numbers, trying to be as broad as possible to meet the specifications of the audience. So for any operating temperatures above 600 Fahrenheit, probably going to switch to a canned or a mag drive pump. One key point about the circulating pump, you do want to protect it against any large particulates, large metal elements, anything that might have gotten into the system. So a Y strainer and a side stream filter is great to protect against any wear that might be caused from that. You'll see that at the pump suction side. So very important, I know we're talking about fluid flow, and you would think that would be a mechanical issue or what you have in your system settings or your pipe size or something hardware. But truthfully, the first and most important element that you can control when talking about fluid flow is making sure you actually have the correct fluid for your application. Now, this is crucial. One of the things that affects fluid flow the most is going to be the viscosity of the fluid itself. So if you have a fluid that's got a really high viscosity to start off, you're going to have really bad flow dynamics and inefficient heat transfer. So what should you look for when you're choosing a heat transfer fluid? So the fundamental product specifications are operating temperature range, obviously, your maximum operating temperature and your minimum operating temperature. You want to make sure that the fluid you're using is well in excess of your maximum operating temperature and can certainly handle your minimum operating temperature. The reason why minimum operating temperature is so important is because that comes into effect with efficient pumpability and fluid movement to allow for heat transfer at that temperature. Maximum operating temperature is more about thermal stability and making sure you don't overheat the fluid. Another key fundamental specification is your minimum startup temperature. Now, you need to take your climate and your environment into account for this property. You want to make sure that if you're operating in a very cold environment where you need to start the system up at some cold temperatures, that your fluid is able to be pumped at that temperature. So obviously, as you would imagine, there's going to be some trade-offs between how high your fluid can go versus how low your startup temperature can go. You need to make sure that you specify a fluid that can handle your entire temperature range. Now, other considerations, levels of impurities in your fluid. You want to make sure you don't have a fluid that's based off of something that's a high level of impurity, so a really dark colored oil, something that's going to be more amber, orange, or yellow. Reason being is those are typically going to indicate a high concentration of impurities that were not purified or distilled out of the fluid itself. This is going to cause increased fouling at higher temperatures, which really affects the flow through the system itself. You want to look for a fluid that, if you need it, will have a specialized additive package, just keeping in mind that those typically narrow the operating range and increase the viscosity of the fluid. And then obviously, if you have a preference to synthetic over mineral oil, you're going to want to make sure that you look into that a little further to make sure your fluid actually meets those criteria. Now, process considerations. If you have an existing system that you're looking to buy fluid for, make sure you don't have any compatibility issues when mixing the existing fluid. Rule of thumb, if you're mixing a synthetic or an aromatic type fluid with a mineral oil, you really want to make sure that you have some kind of proof or certification that they are compatible products. You should do that whenever you're switching brands, if that's the case. You can cause all kinds of problems with cavitations, pressure fluctuations, if you have two different fluids that aren't miscible. Are you running a continuous process? And continuous exposure to high temperatures will lead to accelerated breakdown. Like we discussed before on startup, your local climate should be taken into account. Is your system open to atmosphere? The oxidation is going to be an issue. It's going to thicken the fluid, creating sludge through the system. And is a heat-cool cycle necessary? That's going to change the type of fluid you'll need. So moving on, we're going to discuss three primary factors that are going to create, that you're targeting for an ideal ratio for product features. These are going to be thermal stability, heat transfer efficiency, and product purity. And as we move through, you'll see how not only are these key elements of the performance of your fluid, but also when taking fluid flow dynamics into account, each one of them has a very unique and important aspect that we need to take into account here. So these three elements, thermal stability, heat transfer efficiency, and purity, are the three things that when a fluid formulator is designing a product for efficient heat transfer, try to balance these three out to the best of their ability. So making sure you maximize your ratio of stability, efficiency, and purity is going to be key. So starting off with the first key element, purification. And the level of thermal fluid purification is not just about toxicity issues. You want to make sure that you have, we talked earlier about low level of impurities. Those impurities are going to catalyze fluid degradation. So they foul out on equipment surfaces much faster than the actual fluid molecules break down. So when you're continuously exposing a fluid to high operating temperatures, you want to make sure you have something that's going to be very pure. You're looking for a fluid that's going to be almost water white or very pale yellow to start off with. If not, you're leading yourself into early degradation. So here's a color chart you can kind of look at to see where the fluid scale goes on brand new fluid purity when you're starting off. So benefits of high purification. You're going to get extended fluid service life if you have a more pure fluid. That's also going to lead to reduction in maintenance activities. Something that's not going to be as good of a base product when you start off with is going to lead to premature fouling, which is going to lead to more maintenance activities that are usually unscheduled. You'll have a lower risk of equipment failure, ties hand in hand with that maintenance activities point. And you're going to have a greater consistency in your performance over the lifespan of the fluid. Heat transfer efficiency, next key element that we were talking about of the three. Now this is a key point. We're going to focus a lot on this when we're discussing fluid flow dynamics. So heat transfer efficiency, how well does your fluid actually transfer heat from your heat source through your system into your heated process? That's the key point. You want to be able to do this and minimize the change in temperature from the heater to the process. That's going to require less energy at the end of the day. So something that's more efficient at pulling heat out of that heater and releasing it into your process itself. And the way that we measure this or calculate this based on fluid properties and system dynamics is we use the inside film coefficient. You'll see denoted as H sub I there. Now the fluid inside film coefficient represents heat transfer efficiency of any fluid at a given set of operating conditions. That's taking into account the fluid temperature, the flow dynamics, and the system itself. So if you're considering all operating conditions to be equal, the fluid with the higher heat transfer efficiency is going to be related through a formulation comparing the inside film coefficients. The higher your inside film coefficient, the more efficient the heat transfer fluid at that given set of operating parameters. So that's a key point. If you're going to be planning to operate your system at 500 degrees Fahrenheit or a range between 500 and 550, you're going to want to calculate what your heat transfer efficiencies are in between or across that range of temperatures. So you want to make sure that the fluid you're using and comparing other products to is actually relevant to the properties that you're going to be operating your system at. So this number and this figure is calculated using well-established correlations between the thermophysical properties and the process-specific flow dynamics. So taking into account your pipe size, your fluid velocity, etc. So getting into that a little bit more, efficiency measured by your heat transfer, or your inside film coefficient, is going to be determined by an ideal combination of four main thermophysical properties. And obviously by thermophysical, I mean properties that are dependent on temperature, that change along the temperature scale. So you want to have an ideal combination of low viscosity, you want to have high density, high thermal conductivity, and high specific heat capacity. Now these properties should be available at any thermal fluid manufacturer that's offering you a legitimate heat transfer fluid product, should have these products across the entire temperature scale use range available for you either on their website, through literature request, or by calling the company themselves. Now, considerable advantage in viscosity, density, thermal conductivity, and specific heat capacity will result in better heat transfer efficiency characteristics at any proposed operating temperature and flow condition. This is where a quality thermal fluid manufacturer comes into play. They have the ability to engineer fluids that will balance the most effective ratio of these characteristics. So when looking at manufacturing a product or designing a product that's going to have high heat transfer efficiency, you need to be able to key in on those properties and maximize the ratio itself. Now you see at the bottom right-hand side of the screen there, three property correlations: the Reynolds number, the Prandtl number, and the Nusselt number. Now, these are all used to calculate the heat transfer efficiency. Now for the purposes of fluid flow dynamics, which is our topic today, we're going to be focusing in on the Reynolds number, which is the element of this correlation that takes flow into account more than anything else. Now keep in mind, flow is extremely important when you're talking about heat transfer. If the fluid's not flowing, it's actually just sitting there baking the fluid and can serve as a really good insulator more than something that's actually transferring your heat. Now moving on to thermal stability. Thermal stability of organic heat transfer fluids is measured by a test method called ASTM D6743. Now what does this mean? Basically, it's an ASTM method that can be used to simulate thermal degradation that occurs at the interior walls of a fired heater tube. Why is this important? Well, if your fluid's not flowing correctly, then you're not going to have the ideal design characteristics that the fluid was designed for. That's going to create a serious issue for degradation at the film layer of your pipe wall or at the film surface of your electric heating element. So what this test does is it actually takes whatever sample of fluid you're interested in determining the thermal stability, and it will take the fluid, put it into an oven in a sealed container that's able to withstand the temperature, and put under a vacuum so oxidation does not come into play. What happens is it simulates the maximum film temperature, so whatever your anticipated maximum film temperature for that fluid will be is the test temperature that you're going to run. For instance, a fluid that has a maximum defined temperature, a film temperature of 650 degrees, that would be the temperature the test is run. Now the fluid sits in that oven for 500 continuous hours at that temperature. Now, you're running this fluid side by side versus either a known or a competitive fluid, or if you're doing research to determine what your best formulation is going to be, you'll run multiple formulations in the same test. It's a relative test. Now, thermal stability is measuring the resistance to the irreversible damages. Now, that's important, irreversible damages. Thermal fluids, yes, while they can be filtered and while they can be recycled, when you really degrade a thermal fluid, those damages are irreversible because you're actually taking away from the thermal efficiency and the thermal values that that fluid is able to maintain. So these irreversible damages to fluid properties that are caused by long-term exposure to heat. That's what this test is measuring. And what it's determining is something called the degree of decomposition. Now what that is it's just giving you a representative number that reflects overall thermal degradation of the stressed fluid. By stressed fluid, we mean the fluid that's been in the oven for those 500 hours at the temperature. So what you're looking for is a fluid that demonstrates a lower degree of decomposition after the test is over. The lower the degree of decomposition, the better the thermal stability of that heat transfer fluid relative to any other fluid tested under identical conditions. So why is that important when you're talking about flow? What we're going to get into in the next section is going to be looking deeper at that film layer, that area of the pipe wall where your fluid's being exposed to the highest concentration of heat flux, and it's also having the highest influence of the friction of the pipe, so it's moving slower against those pipe walls. Now that's conditions that are setting you up for overheating the fluid. Basically what you have there is the highest concentration of heat at the slowest area moving fluid. So we need to make sure we pay special attention to that area and how we can maximize our performance there so that we don't prematurely degrade fluid. The higher the thermal stability of the fluid, the more efficient the fluid's going to be at transferring heat away from that pipe wall, and that's going to change your flow dynamic situation and give you better efficiency and lower energy that you would need to actually move that fluid energy. So now getting into the real main topic of today and talking about bringing this all together, those three main properties and how they relate to fluid flow dynamics. So keep in mind here, this is a really key point. What is heat transfer really? And simplify it down, it's energy movement. Heat is energy, plain and simple. If you want to move that energy from one area to another, you need to have proper flow to be able to have that movement. So let's take a look at what typical heat transfer energy movement looks like. Okay? You start off with your heat source, your burner, your electric heating elements. Now that energy from that heat source has to make its way through a solid surface. So you're looking at a pipe wall, a jacket, a heated coil, heat exchanger surface. So the energy from your heat got to move across a solid surface. That's going to be moving into your thermal fluid. Now your thermal fluid has to efficiently take that heat energy hold on to it, and then release it out to your heated process, whatever that may be. So you can see having all this energy movement, and this isn't even taking into consideration the movement and the flow of the fluid itself. This is just going through conductive heat transfer through surfaces and through materials. So our critical focus here, the heated pipe wall, or for that matter, any heated surface when on the other side is your system heat source. So like I said, a tank, jacket, heat exchanger surface, electric heating element. But for our purposes, we're going to be really focusing on heated pipe walls. So your heat source is the highest energy concentration area in your system. The primary area where the thermal fluid is most prone to thermal breakdown. Now, the point here is when we talked about minimum startup temperature, we talked about minimum operating temperature. Well, we define minimum operating temperature as the point in which the fluid is flowing at a high enough rate and at a level where the viscosity is low enough to yield turbulent flow. You do not get efficient heat transfer without turbulent flow. You don't have efficient heat transfer, you're not going to be pulling that heat energy out of the heater. So how do we determine turbulent flow? Well, turbulent flow, for our purpose, is going to be determined by the property we discussed earlier called the Reynolds number. This is a dimensionless number that's going to account for the movement or inertia and the viscous forces of the fluid to identify the state of fluid flow. So the higher the Reynolds number, the more turbulent the flow, the more energy movement, the more washing away of the heat from the surface into the fluid. And that's going to yield better heat transfer. So the key number for turbulent flow regime, you want to have a Reynolds number above 10,000. Okay? So when you look at how a thermal fluid manufacturer defines their minimum operating temperature, you're going to have that to be where the fluid conditions under most typical system designs is going to give you that turbulent flow, that minimum turbulent flow. So what is the Reynolds number? How do we determine that Reynolds number? Well, like we said, it accounts for both the inertia and the viscous forces of the fluid. So movement of fluid is going to be determined by how much area it has to move within. So the inside pipe diameter is the first element. Next item that takes into account for Reynolds number is going to be the fluid density. Now, when you think about density, it's how tightly are the molecules packed into that fluid. Okay, so we talked about energy as just heat movement, and you need to be able to move that heat across not only a pipe wall, but across the fluid molecular structure as well. So the tighter you have your fluid molecules packed in, which is denoted by a higher density, the better your heat transfer across the fluid itself. The next element is going to be your dynamic viscosity. So for all intents and purposes, how thick or thin or what's your resistance to flow at that point for your fluid at the temperature you're operating at. And of course, when you're talking about fluid movement, you have to know what your fluid velocity is going to be, determined by your flow rate and your pipe diameter. So now your viscosity is a key point here. When you have a thicker, colder fluid, a more viscous fluid, you're not going to have great flow, and you're probably going to lead to lower turbulence in your flow regime. So let's sum this up a little bit here. Flow and degradation. Now this really all relates back to the first law of thermodynamics. We talked about heat. Heat is energy. And the first law of thermodynamics applied to how we have it here. Any heat energy that is not transferred out of the heater via bulk fluid movement needs to go somewhere. Okay, so energy is neither created nor destroyed. That's the first law of thermodynamics. And your heater set point is going to be, if you're operating under normal conditions, a set value. And that heat energy is going to be output by your flame or your heat source. If you don't have proper movement of your fluid to pull that heat away from the heater, the energy is going to go somewhere. And where it's going to go is going to be into breaking your fluid molecular bonds. So if you don't have proper flow dynamics and turbulent flow, not removing that heat and moving it elsewhere, it's actually going to be concentrated in breaking down your fluid. This is going to result in cracked or overheated fluid. This creates a serious issue in any system because when you crack your fluid, not only do you decrease the efficiency of it and create unsafe areas, you actually will foul the fluid into the system, creating even more issues, maintenance issues down the road, decreased flow dynamics, and just a compounded problem. Now, where does this energy transfer take place the most? We talked about this. We're going to hit home once again, the film layer. We said the highest heat flux plus fluid flow substantially lower along that pipe surface. Now, what contributes to low Reynolds number? Well, obviously, your set points and your flow. We'll consider that a constant for now. We'll assume that you have operating specifications that are defined by what your process needs. So we're just going to look at the fluid viscosity for our purposes. If you have a really high fluid viscosity, either inherently it's just a high viscosity fluid, or you're operating at high heat with a cold, slow-moving fluid, that's going to give you a low Reynolds number and increase your potential to crack the fluid. We talked about set point for fluid flow rate. Now, again, here's a key point we'll bring back to the beginning when we talked about fluid flow and making sure you select the proper fluid. Now, if you have a set point that you have operating for your fluid flow rate, but you have a fluid that's not really designed for what your purposes are, you're going to have problems right there from the start. And again, a really serious problem, once your system degrades, or if you're not properly starting and shutting down, you have stagnant flow or flow that's impeded by plugged lines due to degraded fluid. That's going to be a serious issue there as well. So let's take a closer look at this from a graphic standpoint. Proper fluid flow. We're going to talk about turbulent and continuous flow here. You want to make sure that you have those two areas, turbulent flow and continuous flow. So the two different areas we're going to look at, you have your turbulent flow thermal profile, and then the opposite of that, a Reynolds number below 10,000 is either going to be transitional or laminar flow. And the good way to think about laminar flow is the fluid itself is kind of moving as a plug through the pipe, okay? So you don't have good movement of fluid. You ever turned on a garden hose and you have it on really low flow and it comes out almost like a clear stream that comes out like a plug almost, versus if you turn on the hose at really high temperatures, high flow rate, and you'll have it coming out and almost spraying all over the place because of the turbulence of that. So the issue with laminar flow is going to be summed up by what we have here. You can kind of see the fluids all moving in one plug area down the pipe. You have all your heat energy focused on the walls, but your fluid's not moving at a turbulent enough level to actually pull that heat away from the walls. So you get all your concentration of that energy on that film layer and not being washed into the bulk of the fluid. So you'll see the highest heat profile against the pipe walls, where the fluid's moving the slowest due to the friction, not being washed out into the bulk area of the system. So laminar flow will kill your fluid. Now, on the contrary, turbulent flow is what we're looking for, and this graphic will show you what you have with turbulent flow. You've got really high movement of fluid throughout the entire pipe. The bulk fluid is being mixed and hitting the pipe walls. Even though it's moving at a more a slower rate against that film temperature, you have that energy being pulled away from the walls so that the entire bulk of the fluid moving through the pipe is actually getting that energy transfer. And that's really important to move the fluid out and you don't crack against the pipe walls. So dynamic fluid movement effectively washes the heat away from the film layer into the bulk area of the fluid itself. That's going to be transferring that energy out of the heat source away from the pipe wall for utilization in your process unit. So what happens when you have your fluid running through a pipe that does not have turbulent flow? We discussed that laminar flow previously. This is really what it looks like. And I said, because that energy has to go somewhere, you have laminar flow and it's not pulling heat away from the walls of the pipe, you're actually going to be putting that energy into cracking the fluid molecules. The energy is going to break the molecules apart at the pipe wall. That's going to create a fouling layer at the film. Here's what that looks like. You get high heat flux at your pipe wall, which is your heated surface. That flux is not being conveyed effectively into the bulk fluid because you're in laminar flow. Therefore, it's not moving out of the heating chamber with efficient heat transfer. So that energy is concentrated at the film layer and is going to be focused on breaking molecular bonds, degrading the fluid at that high area of heat, compounding the problem even further. Your fluid breaks down. When you have broken molecular bonds, your fluid fouls onto the pipe surfaces, degrading into a carbon layer and creating a decreased, not only inefficient heat transfer, but now you have a layer of carbon fouling area or varnishing against your pipe wall itself. So as that builds up over time, due to the compounded problem, you're going to actually decrease the diameter of your inside of your pipe. And you're going to be creating a layer of insulation between that heat source and the bulk movement of the fluid. So some additional flow considerations that you need to take into account. Your pressure differentials through your heater. Okay, so typically most modern heaters have a known pressure differential, and you'll see a pressure differential switch that will, if you drop below a certain level, may trigger an alarm or shut your heater down. Pressure differentials are important because if you don't have proper flow going through your heater coil, you're actually going to increase your pressure. Okay, so the issue with that is you're going to have serious problems if you have too low a flow as well, because you're not actually having enough fluid in there to move the heat out. Important flow consideration, your pumps, okay? So sizing your pump, you want to make sure that you have, if you don't have a pre-packaged skid unit where the pump is sized for the heater size and everything else you're using, you need to make sure that you work with your pump manufacturer. Let them know what your fluid viscosity, your fluid density, all your fluid profile or properties are going to be. Make sure you size your pump correctly for the system that you're utilizing. You need to worry about pump cavitation. If you have immiscible fluid, you have moisture in your system, you severely break the fluid down, you can have to worry about cavitation. We're going to get into in the next couple of minutes here what cold spots are, determined by low flow areas. Cold spots are a serious problem. That's actually the efficiency that you are looking for out in your system, being determined by block sections versus free sections, which will give you better heat transfer. So block sections of your system, the friction factors based on your pressure drop throughout your pipe and also at the fittings throughout the system. And then you really need to worry about extreme low flow. So you have insufficient volumes. You could possibly crack your heater tubes and cause a fire. That's why flow is so important. Safety aspects, efficiency aspects, and maintenance aspects, everything else goes in with flow. So here's a real basic layout of a system design. Okay, you have, and again, I've only included really basic elements here. So don't go out and use this as a blueprint to set up a system. There's some missing elements. But for these purposes, to show you what I mean by cold spots and restrictions and what can happen here, we're going to look at a 3-user continuous loop with one heater. So for example, let's say we have a tank farm and you're heating tanks out in the yard, and you need to have all 3 tanks heated by the same continuous thermal fluid loop. Okay, should be designed to the point where you get accurate temperature control at each user, and your heater and your pump are adequate to move the fluid and heat the fluid to the properties you need them at. So you have your heater, you have your pump, an expansion tank, and your 3 process users. So your heater is going to be that highest level of heat source. And as the fluid moves away from the heater and out into the system, assuming turbulent flow, assuming you have the proper fluid for the design specs you need, you should get consistent heating throughout your system. Obviously, your fluid's going to lose heat energy as it goes through the tanks and goes through the piping. You can combat that some with insulation in your pipes, but if your fluid's not losing heat into your users, you're not effectively transferring heat out to where you need it to be. So it's always going to come back to the heater at a lower temperature than it came out. So what happens is you're going to lose flow in certain areas of a system just inherently by the friction factors in the pipe, your head loss, your pressure loss, and then you have minor losses in certain areas as well. So that's what a system looks like under great flow dynamics, good delta T from the heater out to the process. Now where you're going to have some minor losses, your fittings, any elbows, any areas of pressure drop throughout the system, through the tank coils, whatever your heated process is going to be, you'll see some losses there. But for this purpose, fittings and elbows are great areas where you see minor losses. Now, even more importantly, these are areas where you have potential particulate or sludge buildup. So when you have sludge creation or carbon particles, they can build up in any fittings or areas where flow dynamics are changed. Manifolds and jumper lines. Whenever you jump from your main system pipeline out into the process that are being heated, sometimes you'll have a reduction in pipe size. You'll have like a braided Teflon or braided stainless steel Teflon type hose, and usually they go from, let's say, from a 4-inch down to a 2-inch diameter. That is an area of flow change and pressure manipulation, and will be a great area where you'll see potential for plugging your lines, pipe reduction, redirection of flow. Your expansion tank. Typically, your expansion tank is out of your circulation loop. It's not part of the main flow of your circulating closed loop system. So what that means is you're not getting turbulent flow through that tank. Now, also that means your tank's going to be at a lower temperature, hopefully. But if sludge is created or you have carbon or any kind of solid particulates, the problem's going to be it'll settle in that expansion tank. And that can go out into the system and create problems for flow down the road. So it'll be really important to make sure you pay attention to what's going on in your expansion tank. You have a low-level switch in there. If you have sludge buildup or particulate settling, you could block that low-level switch. So you need to pay close attention to what's going on inside the expansion tank. And the heater coil and elements themselves. The fluid fouling restricts flow. So as you break down that fluid inside the heater tube, it's going to actually restrict the flow. It's going to take your diameter of your pipe coil and decrease it. If you have electric heating elements, you're actually going to create a carbon shell on the outside of the electric elements or sludge blocking that line and having improper flow. So a cold spot. Great way to tell this is if you have multiple sections of your system that are typically operating at certain temperatures, and for this example, you have your specific section that's not reaching temperature is tank 2. You have 3 tanks all running together. All of a sudden, for some reason, tank 2 is not getting heat. Tank 3 is, which means that you have some kind of blockage or something restricting your flow into tank 2. That's going to be flow restriction that's creating all kinds of problems throughout the rest of the system. So that's a great indication where you have a blocked line. So how do we prevent degradation that causes those blocked lines? So we need to make sure that we understand fluid degradation is going to happen. And when it happens, your safety margin is going to go down, and the maintenance that you have to do is going to go up. So over time, degradation is inevitable. We just want to minimize the rate which happens. So first and foremost, issues that impact fluid in the system. Thermal cracking, overheating the fluid. And that's going to be really determined by proper startup, shutdown, and operating conditions. Obviously, oxidation happens in the expansion tank where it thickens the fluid and creates a reaction, and contamination of the fluid. A key maintenance practice, we're going to focus on fluid analysis. So visual degradation, obviously as the fluid gets darker, it doesn't necessarily mean that you have a degraded fluid, but if you have a lot of a higher viscosity, that's visual, you have a lot of sediment buildup, that's a pretty good indication of degraded fluid. Now obviously as your viscosity increases and your particulates pick up, your flow dynamics are going to change. That's going to affect everything at the film layer, which is also going to affect the heat transfer efficiency. You're going to be running an inefficient process at that point. So thermal cracking, it occurs when too much heat is applied to the fluid and molecular bonds are broken. We had the visual example of that earlier. This leads to the formation of low boilers or a lower viscosity fluid. You'll have a problem with pump cavitation, possible seal problems. Excessive low boilers can reduce your flash point or your auto ignition temperature, which is a serious safety issue. And you're going to have reduced heat transfer efficiency. Now, compounded problem here, what you're going to run into is as your fluid breaks down, fouls onto the system walls or pipe walls, it's going to reduce the heat transfer efficiency out of your heater. So even if your set point is, let's say, 500 degrees, and all of a sudden your fluid now, because you're getting resistance to proper heat transfer and flow inside the heater, the fluid's actually coming out at 485 degrees. So the natural reaction of an operator is going to be to increase the set point temperature to get the fluid temperature to what you need at your process user. That's just going to compound the problem because now you're putting more heat onto a degraded fluid. So what are your probable causes? Low flow, we talked about that. Flame impingement, so where the flame is on one side of the heater more than the other. Excessive recirculation through the heater, and improper startup and shutdown. And that's really influenced by flow more than anything else. So preventing thermal cracking. We talked about this before. Ensure that your fluid is designed for your maximum operating temperature. Key point, the Arrhenius factor. If your operating temperature is 18 degrees Fahrenheit over the recommended max bulk temperature that your fluid manufacturer recommends, your fluid life will be cut in half. So if you're 40 degrees over, you can cut that in half again. You can see how it's a vicious circle as you start overheating too much and your fluid breaks down. You always want to make sure you maintain your design flow rate. That design flow rate is there for a reason. It's to give you proper heat transfer, high enough turbulent flow to move the heat from the heater out to your process. And always follow proper startup and shutdown procedures. So what are our proper startup and shutdown procedures? Well, we talked that low temperatures, higher viscosity fluids are not thermally efficient because they're not giving you turbulent flow that you need. If you apply quick temperature rises, you will crack thermal fluid at the heated surface itself. So you need to be able to start up slowly to keep the heater from going into high fire until your fluid viscosity drops to around 10 centipoise. And that's just a rule of thumb. You really need to see your fluid and equipment manufacturer for this recommendation. But typically 10 centipoise under normal operating conditions in traditional systems will give you that Reynolds number that allows for turbulent flow. But once that turbulent flow is reached, you can raise your set point in higher increments to give you the designed operating temperature. So that 10 centipoise for a mineral oil-based fluid is going to be around 180 degrees Fahrenheit. And if you can just look at your viscosity versus temperature chart or table, you can find what that number is going to give you that 10 centipoise. Proper system shut down. Now this is really key here. If you turn the circulating pump off while you're at high operating temperatures, you're actually going to raise the temperature above the max bulk temperature of the fluid and have severe thermal cracking within the heating chamber. So imagine you have a fluid flowing through your heater coil out into the system, and all of a sudden you just decide to turn the circulating pump off at the same time you turn your heater off. But now your fluid is sitting stagnant, not removing any of that heat energy that's built up in that heater chamber. And you're just going to be cooking the fluid right on there. It's kind of the equivalent of having cooking something on a stove top and leaving it sit there under high fire and not stirring it. You're basically just having it sit there and take all that heat energy in to break the fluid apart. So how do you combat that? You keep your main circulating pump operating at all times when the heater is powered down. Once the fluid gets to around below 200 degrees Fahrenheit, then you can shut the circulating pump off because enough energy is out of the heater. All right, so how do we determine all of this, though? You don't have a view or a screenshot or any way to really look inside your heater coil, so you need to have a fluid analysis program. It should be managed by your heat transfer fluid supplier. So it's the most reliable tool you can have for understanding the optimal level and avoiding any unexpected problems. Recommended annually as a minimum preventive maintenance practice. Fluid analysis can really tell you what's going on, check to see if your viscosity is increased or decreased, if you have any oxidation issues, any low boilers being formed, and that will really help you determine anything that's going on at the molecular level and at the physical bulk level of the fluid in your system. What you need to do is make sure that if you have any problems, you're seeing decreased temperature outputs or you're getting cold spots in your system, the first thing you should do is have a sample tested by a professional heat transfer fluid analysis lab. Key point, don't do it with a lube oil analysis. The tests are different. They should be specific to a heat transfer fluid. But you could have some serious flow issues. You could have some serious degradation blocking lines. If you have cold spots or you're seeing inefficient temperature out of your heater, get a fluid analysis done. You'll be able to determine what the problem is and fix the problem right ahead. So if you do have an issue with fluid analysis, you should really make sure you verify that with your fluid analysis program. 2 distinct methods to clean it. You can fix those cold spots by a dedicated solvent cleaner or an on-the-fly additive cleaner. Just make sure that any disposal of waste oil needs to be considered. All local regulations are different how they treat waste oils. If you have a synthetic product, it could be even more different than that. So really work with your thermal fluid manufacturer and supplier when you're dealing with cleaning and recycling oils. So really, what it all comes down to, improper flow, impact of fluids on operations, these are all designed to be very safe, very efficient, low maintenance products, the reason the technology exists. That's considering the fact that your equipment design is correct and you're using the proper fluid under the proper conditions. You need to protect your people, safety of your plant, your investment, the equipment and the fluid, your efficiency, and avoiding downtime. Always make sure you select the right fluid. Not doing that, you'll get accelerated degradation, improper flow dynamics, equipment failures, fouling on the surface, decreased efficiency, and increased maintenance. If you're operating outside of your design specifications and you're failing to adhere to basic maintenance practices, that's going to lead to those irreversible damages of the fluid and the equipment. You have the highest stability fluid out there, but if you're operating it inefficiently, it will break the fluid down prematurely. And your primary concern, when you run properly with a properly designed system with the correct fluid, this technology is safe and low maintenance. But the inherent dangers of a high temperature operation increase exponentially when these factors are taken for granted. Make sure you work with somebody reputable, a consultant, a manufacturer, a supplier, rep. Select something high quality. Make sure it was actually engineered, and they can prove to you that it was engineered fluid for your design specifications. And you should be able to co-develop an operation-specific preventative maintenance plan with your manufacturer or supplier of heat transfer fluids. It's going to give you a much higher return on your investment. It'll prolong your fluid life, decrease the potential for fouling, operating issues, and changeouts. And this critical element of your operation is going to run with increased safety, efficiency, and reliability without high demand on your personnel. So thank you very much. Now we'll take some time for questions if anyone has any. Gabrielle, I'll turn it over to you for some questions.
Okay. Yes, we have lots of great questions, Ryan. One question is, how thermal cycling affects the life of thermic fluid in a batch distillation process operating at a range of temperature for each batch?
Okay, so key point you want to make sure you have there. If you're cycling, your thermal cycling is giving you extreme temperatures on one end or the other, you need to make sure that you have a specialized fluid that can handle that entire temperature range. You don't want to be operating at the minimum or the maximum. Now, there are specified heat/cool fluids that have a much wider specified temperature range. You'll usually end up paying a bit more for them because they're higher performance. But it's well worth it because that fluid will last much longer. Cycling can really affect the fluid more so because usually when you cycle, you're going to one extreme or the other. You're trying to operate the fluid, you're pushing the limits at the low end or you're pushing the limits at the high end. One other key point between cycling with a batch process, we talked about fluid flow and startup and shutdown procedures. When operating a batch process, startup and shutdown become much more important because you're cycling through those operations more frequently. So you really need to make sure you take the time to operate under the proper startup and shutdown procedures we discussed. Ramping your temperature up slowly, running your circulating pump after your heater's turned off so that you don't damage the fluid in that heater area.
Okay. Another question. Some systems have a deaerator tank. Does this tank contribute to the oxidation of the fluid?
Okay, so for a deaerator tank, the purpose of that is usually a system with a deaerator tank might also have like a thermal buffer tank on it. And what you'll see with the deaerator tank, you're actually looking to, it runs the fluid through a system in that tank to remove any areas for oxidation. It's actually designed to prevent oxidation more than anything. So what the proper design for that's going to be is that it allows the fluid itself to, what you don't want to have happen is that fluid in that deaerator section be at a high elevated temperature range, because that's going to be where your oxidation is going to come into play. So yeah, the deaerator should be designed, if it's a deaerator tank from a properly designed thermal fluid system manufacturer, you're not going to really contribute to oxidation too much. What you're going to do though is you really need to pay close attention to what your temperatures are in your expansion reservoir. You really need to make sure that you have any moisture that might be built up in that area is removed. And you probably should look, if you're at high temperatures running through a system with a deaerator tank, look to have a nitrogen blanket put on the system itself. But the design itself is actually really good, and it is value added just as long as you make sure you're operating it efficiently.
Great. How important is the net positive suction head for a pump in this type of closed loop system?
It's going to be something that you really need to make sure you work with your pump supplier with. Typically, when you're looking at a thermal fluid system, there's some general design aspects that are pretty much constant throughout any design. So, like I said, your most common pump that you're going to be using is a centrifugal pump. So, taking that into account, you need to make sure that your design is correct. Now, that being said, unless you're using a fluid that's really out of the range of the norm, something with a really high viscosity, or you've degraded your fluid to the point where it's not going to be efficient anymore, your design features for your system should be well equipped to handle any typical process. So the pump manufacturer, the equipment manufacturer that included that pump is going to probably have taken those design elements into account prior to you implementing into your system. But working with a pump manufacturer and having really a great working relationship with all the elements of your equipment, your pump manufacturer, get to know who the rep is, get to know who the manufacturer is. Your heater manufacturer, same thing. Have a service rep come out and look at it and really get to know your fluid manufacturer and make sure that they can tell you these things and work with you on it. It shouldn't, it's nice to have one single source, but having the ability to work with all of them individually will help you out in the long run.
Thanks. Okay, here's another one. On startup, what is the typical heating rate until turbulent flow is reached?
So you should probably ramp it up around 10 to 20, depending on what your temperature is. So obviously you're getting up to 600 degrees. Once you reach turbulent flow around 180, I'd say between 10 to 20 degrees Fahrenheit at a time, you should ramp up until you get to that point. That's going to be a nice even flow, or a nice even temperature ramp until you get to turbulent flow. What you don't want to do is shock your fluid and have that immediate high heat flux going into the film layer. So 10 to 20 degrees, I would probably err on the side of 10 degrees at a time until you get to 180.
Okay, great. This is another good question. When we are flushing a system, we use the kinematic viscosity to calculate Reynolds number. Is this a more accurate method for Reynolds number rather than dynamic viscosity?
And it depends on what your other properties are. You just need to make sure when you're calculating the Reynolds number, it's a dimensionless value, okay? So if you're using the kinematic viscosity and your other properties are using, you're not actually using the fluid flow rate, that's going to be an issue. The way that we calculate Reynolds number by using the dynamic viscosity takes the density of the fluid into account and the velocity of the fluid into account. So what you really need to make sure is you're canceling your unit operations out. So yes, either number can be used as long as the other factors that you're including in the formula are going to cancel out your units. So you really have to pay attention to that. You can't just plug in a viscosity number. You have to actually know what those units are and make sure they cancel out with both your density, if you're using density, and your velocity of your fluid.
Great. I think we have time for one last question, and this one is, how would excessive recirculation through the heater create fluid degradation? I can see how low fluid would cause excessive residence time in the area near the heater, but high flow?
So if you have too high a flow going through your system, you're actually not efficiently pulling the heat out of the system. You're flowing it through much too quickly to actually have residence time to pull the fluid out. So when you have that excessive recirculation of the fluid, you're not going to be having efficient heat transfer out in the user process, and what you're going to do is you're going to be changing your temperature set points up higher to be able to compensate for that. So when you have a temperature set point above what your design maximums are going to be, then you can really have a problem at the film layer. Because remember, when you're pulling the fluid out, it's at the bulk layer. That's a bulk movement of your fluid. So if you have fluid that's moving through that system way too fast, you're not going to be efficiently picking up the heat, and you're going to have set points that are beyond what the film layer can take, and that's where your degradation happens.
Great. Thanks, Ryan.
Absolutely. Thank you. And thank you everybody for paying attention and listening, and hopefully you got something out of everything. And if you have any other questions or need to work with us offline, please feel free to contact us.